What if the passage of a single second depends on where you are and on what surrounds you? And what if there are places in the cosmos where time slows so dramatically that from the outside, it almost appears to stop? Most of the time, time feels simple. It flows forward at a steady pace, measured by clocks, marked by motion, and shared equally by everything around us. A second feels like a second whether it passes on Earth, in orbit, or in the quiet space between stars. Yet modern physics has revealed that this sense of uniform time is not a fundamental feature of the universe. Time can slow, stretch, and bend depending on where you are and what surrounds you. Few objects challenge our understanding of time more profoundly than black holes. Born from the collapse of massive stars, these extreme regions of space reshape gravity to such an extent that the familiar rules of motion and duration begin to break down. Near a black hole, time itself behaves in ways that appear almost paradoxical. Clocks do not agree with one another. Events unfold differently depending on who is watching and from where they observe. The idea that gravity could influence time emerged only in the last century. Before that, time was assumed to be absolute, ticking forward at the same rate everywhere in the cosmos. That assumption changed with the development of general relativity, which revealed that massive objects warp not only space, but time as well. The stronger the gravitational field, the more slowly time passes relative to regions of weaker gravity. Nowhere is this effect more dramatic than near a black hole. From a distance, a black hole may appear calm and unremarkable, distinguished only by its influence on nearby stars and glowing disks of hot gas. But as one approaches its boundary, known as the event horizon, the flow of time begins to diverge sharply from the rest of the universe. To a distant observer, processes near the black hole appear to slow almost to a halt. To an observer closer in, time seems to move forward normally, at least at first. This difference in experience lies at the heart of how black holes affect time. Understanding these effects requires stepping away from everyday intuition and into a universe governed by relativity. It means accepting that time is not a single universal rhythm, but a local experience shaped by gravity and motion. Around black holes, this truth becomes unavoidable. They serve as natural laboratories where the deepest ideas of physics are pushed to their limits, revealing both what we understand and what remains unknown. Time does not simply exist on its own. It is woven into the structure of the universe, linked inseparably to space and shaped by gravity. To understand how black holes affect time, it helps to begin with a principle that governs all motion and all clocks, the idea that time is relative rather than absolute. According to general relativity, massive objects curve space-time around them. This curvature affects how objects move, how light travels, and how quickly time passes. Near a massive body, time slows compared to regions farther away. This effect is subtle near Earth, but it becomes extreme near dense objects such as neutron stars and black holes. In these environments, gravity is so intense that the difference in time flow becomes impossible to ignore. Even far from black holes, the relativity of time has been measured and confirmed. Clocks placed at different altitudes on Earth tick at slightly different rates. Satellites in orbit experience time differently than instruments on the ground, an effect that must be corrected for navigation systems to function accurately. These small discrepancies are the same phenomenon that becomes dramatically amplified near a black hole. A black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. As the core contracts, gravity strengthens, compressing matter into an ever smaller volume. When the collapse passes a critical threshold, no known force can halt it, and the result is a region of spacetime where gravity becomes overwhelming. The boundary of this region is the event horizon, a surface beyond which light itself cannot escape. As an object approaches a black hole, the slowing of time becomes increasingly pronounced. To an observer far away, a clock falling toward the event horizon appears to tick more and more slowly. Each second stretches longer than the last, and the object seems to freeze in place as it nears the boundary. This effect is not an illusion of malfunctioning clocks, but a genuine difference in how time flows in strong gravitational fields. From the perspective of the falling object, however, time continues to pass normally. The clock it carries ticks steadily, and physical processes proceed as they always have. This contrast between the distant observer and the infilling observer reveals one of the most striking consequences of relativity, that time itself is not shared equally across the universe. This disagreement between observers is not a contradiction, but a reflection of how gravity reshapes spacetime. Each observer experiences time locally, influenced by their own motion and the gravitational field around them. Near a black hole, these differences become extreme, exposing the limits of everyday intuition about cause, sequence, and duration. The slowing of time near a black hole is known as gravitational time dilation. The closer an object moves toward the event horizon, the stronger the curvature of spacetime becomes, and the more slowly time passes relative to distant regions. Mathematically, this effect grows without bound at the event horizon itself. From far away, it would appear that time at the horizon slows toward zero, never quite reaching it. Light emitted from an object falling toward a black hole also reveals this effect. As light climbs out of the intense gravitational field, it loses energy and shifts toward longer wavelengths. To a distant observer, this gravitational redshift makes the object appear dimmer and slower, its signals stretched over longer intervals. Eventually, the light becomes so redshifted that it fades from view, reinforcing the impression that time has frozen at the edge of the black hole. Yet nothing physically special occurs at the event horizon for the infilling observer, at least in the case of large black holes. There is no sudden wall or dramatic boundary. The laws of physics continue to operate locally as before. Time flows normally on the falling clock, even as the rest of the universe appears to evolve increasingly quickly outside. Stars may seem to age, galaxies may shift, and cosmic history may unfold at an accelerated pace relative to the observer nearing the horizon. This reversal of perspective leads to a strange conclusion. From far away, the falling object never crosses the event horizon. From its own point of view, it does so within a finite amount of time. Both descriptions are valid within their own frames of reference. There is no single universal timeline that reconciles them, only different experiences shaped by gravity. Inside the event horizon, the role of time and space undergoes an even more radical transformation. According to classical general relativity, all paths lead inward toward the singularity. What was once a spatial direction becomes unavoidable, much like the forward direction of time outside the black hole. In this sense, falling toward the center is not a choice, but a progression built into the structure of space-time itself. As matter continues inward, tidal forces grow stronger. These forces arise because gravity pulls more strongly on parts of an object closer to the black hole than on parts farther away. Over time, this stretching effect can become extreme, elongating objects along the direction of fall. While this phenomenon is often described in dramatic terms, its significance lies in how it reflects the steep gradients of space-time curvature near the center. Approaching the singularity, the known laws of physics begin to fail. Density and curvature rise beyond the limits where current theories can make reliable predictions. Time, as defined by measurable intervals and orderly progression, may lose its meaning entirely. Whether time ends, loops, or transforms into something unrecognizable at this point remains unknown. Because of these uncertainties, black holes occupy a unique place in modern physics. They are regions where gravity, time, and quantum effects intersect in ways that challenge existing theories. Understanding how time behaves near and inside black holes is not just about describing extreme environments, but about probing the foundations of reality itself. The effects of black holes on time extend beyond their immediate surroundings. Even at great distances, their immense mass influences the flow of time in subtle but measurable ways. Any object orbiting a black hole experiences time more slowly than it would far from any massive body. The closer the orbit, the stronger the effect, creating a gradient of time that varies smoothly with distance. This becomes especially important in the regions just outside the event horizon, where matter often forms a rapidly rotating accretion disk. Gas and dust spiral inward, heating up as friction and compression raise temperatures to extreme levels. As this material orbits at significant fractions of the speed of light, another form of time dilation comes into play. According to special relativity, motion itself slows the passage of time. Near a black hole, gravitational time dilation and velocity-based time dilation combine, producing some of the strongest time distortions known in the universe. For matter in the inner accretion disk, time may pass far more slowly than it does for distant observers. Processes that take seconds locally may appear stretched over minutes or longer when viewed from afar. These effects influence the timing of radiation bursts, the flickering of X-rays, and the behavior of jets launched from the vicinity of black holes. By studying these signals, astronomers can indirectly measure how time behaves in extreme gravitational environments. Supermassive black holes, found at the centers of galaxies, provide particularly striking examples. Although their event horizons are vast, sometimes larger than the orbit of Mercury, the gravitational effects near them remain intense. For these black holes, the region where time dilation becomes extreme lies well outside the central singularity, making it possible for matter to experience profound time distortion without immediately encountering destructive tidal forces. This distinction matters because it allows objects to approach very close to the event horizon of a supermassive black hole while remaining intact for a time. In such scenarios, an observer could experience a significant divergence between their own clock and the clocks of the distant universe. While minutes pass locally, faraway centuries could unfold. The precise ratio depends on distance, mass, and motion, but the principle remains the same. Gravity reshapes time. Rotating black holes introduce additional complexities. Most real black holes are expected to spin, carrying angular momentum from the stars that formed them or the matter they have consumed. Rotation drags spacetime itself, a phenomenon known as frame dragging. Near a rapidly spinning black hole, spacetime is pulled along with the rotation, affecting how time and space are experienced. In these rotating systems, the boundary between what can remain stationary and what must move becomes blurred. Outside the event horizon lies a region called the ergosphere, where spacetime is dragged so strongly that no object can remain at rest relative to distant stars. Time in this region behaves in unusual ways, shaped not only by gravity, but by the twisting of space-time itself. Frame dragging alters the paths of particles, the flow of energy, and the structure of time near the black hole. It also enables processes that extract energy from the black hole's rotation, linking the behavior of time to the dynamics of cosmic power sources. These effects demonstrate that black holes influence time not as static objects, but as active, evolving features of space-time. Through observations and theoretical models, physicists continue to refine their understanding of how time behaves near black holes. Each new measurement provides another piece of evidence that time is not an absolute backdrop, but a flexible dimension shaped by mass, motion, and geometry. Near black holes, this flexibility becomes impossible to ignore. The influence of black holes on time also raises deeper questions about causality and the order of events. In everyday experience, cause clearly precedes effect, and the sequence of moments feels universal. Near a black hole, this familiar ordering can become ambiguous. Because different observers experience time at different rates, they may disagree not only on how long events take, but on when those events occur. Signals sent outward from near the event horizon become increasingly delayed and distorted. From a distant viewpoint, messages appear to slow, stretch, and fade, arriving less frequently as the source approaches the boundary. This creates a kind of temporal isolation. Events that unfold normally for the local observer become effectively sealed off from the rest of the universe, not because time has stopped, but because it flows along a path that no longer reconnects. This separation has important consequences for information. In classical descriptions, anything that crosses the event horizon is lost forever, taking with it the details of its past. Time continues inward, but never returns. This idea leads to what is known as the information paradox, a problem that arises when the irreversible flow of time inside a black hole conflicts with the time-symmetric laws of quantum mechanics. According to quantum theory, information about physical systems should always be preserved, even if it becomes scrambled or difficult to recover. Black holes challenge this principle by appearing to erase information permanently. If time inside the black hole ends at the singularity and nothing escapes, then information seems to vanish from the universe. Resolving this tension requires rethinking how time, gravity, and quantum processes interact. One proposed resolution involves black hole evaporation. Over extremely long periods, black holes are predicted to emit a faint form of radiation, slowly losing mass. This process, known as Hawking radiation, implies that black holes are not entirely timeless prisons. Instead, they evolve over immense timescales, gradually shrinking and eventually disappearing. If this is correct, then time continues to operate even at the edge of what appears to be absolute darkness. The timescales involved are extraordinary. For stellar mass black holes, evaporation would take far longer than the current age of the universe. For supermassive black holes, the duration stretches beyond comprehension. Yet the existence of this process suggests that time near black holes is not frozen forever, but stretched across spans so vast that they challenge ordinary meaning. These ideas remain incomplete. A full theory of quantum gravity, capable of unifying general relativity and quantum mechanics, is still unknown. Until such a framework is found, the true nature of time inside black holes remains one of the deepest open questions in physics. What is clear is that black holes force time into unfamiliar shapes, revealing that its flow is not a fixed feature of reality, but a dynamic aspect of the universe itself. Another way black holes reshape time is through their impact on the future of the universe itself. Because they slow time so dramatically near their boundaries, they act as reservoirs where processes unfold at radically different rates than elsewhere. In a cosmos governed by relativity, this means that black holes do not simply exist within time, they actively sculpt how time is distributed across space. As stars, gas, and even other black holes fall inward, their histories become increasingly compressed from an external perspective. Entire lifetimes can appear to stretch toward infinity as they approach the event horizon. This creates a striking contrast between regions of rapid cosmic evolution and regions where change seems suspended. Over billions of years, this uneven flow of time influences how galaxies grow, merge, and reorganize. In cosmology, black holes are sometimes described as anchors of deep time. While stars burn through their fuel and galaxies evolve, black holes persist. Their longevity means they remain long after most luminous structures have faded. In the far future, when star formation has largely ceased, black holes may be among the last significant structures left behind. During these epochs, time near black holes will still be flowing differently than in the vast, empty regions between them. Some theories suggest that black holes may even preserve traces of earlier cosmic eras. Because time slows near their horizons, they could act as windows into the deep past when viewed from afar. While this does not allow observation of ancient events in any practical sense, it highlights how black holes entangle time with history, stretching moments across cosmic scales. Speculation goes further when considering what lies beyond the singularity. In certain theoretical models, the interior of a black hole may connect to other regions of spacetime. Some solutions to Einstein's equations allow for tunnels or extensions where time continues in unfamiliar directions. In these ideas, the end of time inside a black hole may instead mark a transition to another phase of spacetime, though no evidence currently confirms this. Other proposals suggest that the singularity itself may not be a true endpoint, but a sign that existing theories break down. Quantum effects could soften the collapse, replacing the singularity with a region where time behaves differently rather than ending altogether. In such scenarios, time might slow, reverse, or branch in ways that cannot yet be fully described. These speculative ideas underscore an important point. Black holes expose the limits of current knowledge. They show that time, often treated as a background parameter, becomes an active player under extreme conditions. The fact that modern physics cannot fully describe time inside black holes does not indicate failure, but rather highlights where new understanding is needed. Even without complete answers, black holes already teach a clear lesson about time. It is not universal, not fixed, and not immune to gravity. Instead, time flows along paths shaped by mass and motion, stretching and warping in response to the structure of spacetime. Nowhere is this more evident than near a black hole, where seconds lose their usual meaning and the future unfolds at different speeds depending on where one stands. As research continues, observations of black holes grow ever more precise. Gravitational wave detectors record the merging of these objects, revealing how spacetime vibrates when extreme masses collide. Telescopes capture shadows cast by event horizons, offering indirect glimpses of how light and time behave at their edges. Each discovery deepens the understanding that time is woven into the fabric of the universe and that black holes are among the most powerful weavers of all. The study of how black holes affect time has practical consequences for understanding the universe on its largest scales. When black holes merge, they do not simply combine their mass. They also merge regions of spacetime where time has been flowing at different rates. The result is a violent reconfiguration of spacetime itself, producing ripples that propagate outward at the speed of light. These ripples, known as gravitational waves, carry information about how space and time were distorted during the merger. As the waves pass through distant regions of the universe, they stretch and compress spacetime, briefly altering the passage of time by minuscule amounts. Although these changes are far too small to notice directly, their detection confirms that time is not rigid, but elastic, capable of being disturbed and reshaped. Gravitational wave observations have provided new ways to test theories about black holes and time. The precise timing of these signals allows scientists to measure how fast black holes orbit one another, how quickly they spiral inward, and how spacetime behaves under extreme conditions. Each detected event adds confidence to the idea that time behaves exactly as general relativity predicts, even in the most intense gravitational environments. Beyond mergers, black holes also influence time through their role in galactic centers. Supermassive black holes regulate the growth of galaxies by affecting the motion of stars and gas over enormous distances. Their gravitational pull shapes orbital periods, alters the timing of star formation, and influences how matter flows across galactic scales. In this way, black holes help set the temporal rhythm of entire galaxies. Time near a black hole is not only slowed, but also unevenly distributed. Two nearby points can experience different rates of time passage if their distances from the black hole differ. This creates gradients in time similar to gradients in temperature or pressure. Objects moving through these gradients experience subtle effects that influence their trajectories and interactions, further linking time to motion. In extreme cases, these time gradients can affect stability. Orbits close to a black hole can become chaotic, with small differences in timing leading to large differences in outcome. This sensitivity highlights how deeply time is woven into the behavior of matter under strong gravity. Motion cannot be separated from duration, and cause cannot be fully separated from timing. The question of whether black holes could ever allow travel into the distant future often arises from these ideas. In principle, strong gravitational time dilation means that someone near a black hole could experience far less time passing than the rest of the universe. If they could return, they would emerge into a future far removed from their point of departure. While this does not violate known physics, the practical challenges make such scenarios purely theoretical. The environments near black holes are hostile beyond current technological limits. Intense radiation, extreme tidal forces, and unstable orbits make survival unlikely. More importantly, returning from regions of extreme time dilation would require precise control over trajectories near the event horizon, something far beyond present capabilities. As a result, black holes remain laboratories for thought experiments rather than destinations. Still, these considerations illustrate how black holes turn time into a variable rather than a constant. They demonstrate that the future does not unfold uniformly everywhere, but can race ahead in some regions while barely advancing in others. This uneven progression reshapes intuition about aging, history, and duration on cosmic scales. In the end, black holes reveal that time is inseparable from gravity. They show that time does not exist independently of the universe's structure, but responds to it. Where gravity is weak, time flows gently and predictably. Where gravity becomes extreme, time bends, stretches, and departs from everyday expectations. by studying black holes, physicists are not only learning about exotic objects, but uncovering the true nature of time itself. As the understanding of black holes deepens, their relationship with time continues to shape how physicists think about the ultimate fate of the universe. Over vast cosmic spans, time itself becomes dominated by slow processes, gradual decay, and rare but powerful events. Black holes sit at the center of this long future, influencing how time unfolds when most familiar structures are gone. In many models of cosmic evolution, the universe expands and cools, stars exhaust their fuel, and galaxies grow quiet. During these eras, black holes persist as some of the last active objects. Their influence on time becomes increasingly pronounced, not because gravity grows stronger, but because everything else slows or fades away. Against this backdrop, black holes become markers of deep time, spanning epochs that dwarf the age of stars and planets. As black holes slowly lose mass through Hawking radiation, the passage of time near them takes on a different character. The radiation process is extraordinarily slow, yet it implies that black holes are not eternal. Time continues to operate, even in environments where change seems imperceptible. The evaporation of a black hole is not an event, but a gradual unfolding across unimaginable durations. During this evaporation, the way time is experienced depends strongly on perspective. From far away, the black hole appears to shrink and fade, its influence diminishing over trillions upon trillions of years. Near the horizon, however, time remains deeply distorted, with processes unfolding at a pace disconnected from the rest of the cosmos. This layered experience of time reinforces the idea that there is no single cosmic clock. The possibility that black holes encode information about the past also ties time to memory. If information is preserved in some form during evaporation, then traces of earlier states of the universe may be carried forward into the distant future. Time, in this view, is not merely a sequence of moments, but a record of transformation, with black holes acting as repositories of change. Some theoretical approaches suggest that spacetime itself may have a granular or emergent nature. In these frameworks, time does not exist fundamentally, but arises from deeper physical processes. Black holes provide testing grounds for such ideas, because the usual flow of time breaks down near their centers. Studying these regions may reveal whether time is a basic ingredient of reality or a phenomenon that emerges from more fundamental laws. The tension between relativity and quantum mechanics becomes especially sharp when considering time near black holes. Relativity treats time as part of a smooth, continuous space-time fabric, while quantum theory often describes processes in discrete steps. Reconciling these views may require reimagining what time truly is. Black holes sit at this crossroads, forcing theories to confront their differences. Even without a complete theory, one conclusion remains robust. Black holes demonstrate that time is flexible. It responds to gravity, motion, and energy in ways that defy everyday expectations. Seconds can stretch into years, moments can diverge between observers, and the future can unfold unevenly across the universe. By examining black holes, scientists are not merely studying distant cosmic objects. They are exploring how the universe organizes change itself. Time, once assumed to be a silent backdrop, becomes an active participant in the cosmos. Near black holes, it bends and reshapes, revealing a universe where the passage of time is as dynamic and complex as space itself. These insights also influence how scientists think about the beginning of the universe. Just as black holes represent regions where gravity overwhelms time in the present cosmos, the early universe appears to have passed through conditions of extreme density and curvature. In these earliest moments, time itself may have behaved in unfamiliar ways, shaped by forces similar to those found near black holes. Studying one may help illuminate the other. In the moments after the universe began, matter and energy were compressed into a state far denser than anything observed today. Under such conditions, the distinction between space and time may have been blurred. Some models suggest that time, as a clearly defined direction of change, may not have existed in the earliest phases. Instead, it may have emerged gradually as the universe expanded and cooled. Black holes, with their extreme gravity, offer modern analogues where this emergence may be partially replayed. This connection raises the possibility that time is not a permanent feature of reality, but one that can appear, distort, and perhaps disappear under certain conditions. Near black holes, time slows and loses its familiar structure. Near the beginning of the universe, it may have been undefined altogether. In both cases, gravity plays a central role in shaping how change is ordered and experienced. Theoretical physicists have proposed that time might be an emergent property arising from quantum interactions. In this view, what is perceived as the flow of time results from correlations between physical systems rather than from a fundamental ticking clock. Black holes challenge this idea by pushing correlations to their limits, isolating regions of spacetime and severing familiar connections between cause and effect. Another line of thought explores whether black holes could give rise to new regions of spacetime altogether. In certain speculative models, the interior of a black hole may lead to the birth of a new, expanding universe, with its own version of time unfolding independently. While highly conjectural, such ideas reflect how deeply black holes intertwine questions of time, origin, and continuity. Observational evidence for these scenarios remains absent, but their value lies in what they reveal about current theories. The fact that black holes permit mathematically consistent solutions where time behaves radically differently suggests that existing intuitions are incomplete. Time may be more flexible and context-dependent than once believed. Closer to observable reality, ongoing measurements continue to refine understanding of time near black holes. Precision timing of pulsars orbiting dense objects, careful tracking of stellar motion near galactic centers, and increasingly detailed images of accretion flows all contribute to a clearer picture. Each observation confirms that time dilation near massive objects is not speculative, but real and measurable. As technology advances, these measurements will grow more precise. Future observatories may be able to detect subtle differences in time flow around black holes with unprecedented accuracy. Such data could reveal deviations from existing theories or confirm them to new levels of confidence. In either case, time remains the central quantity being tested. Ultimately, black holes serve as reminders that time is not a passive backdrop. It is shaped by gravity, influenced by motion, and altered by the structure of spacetime itself. Near black holes, time becomes something that can stretch, slow, fragment, and perhaps even lose its meaning entirely. By confronting these extremes, physics gains insight into the ordinary as well. The steady passage of time experienced on Earth is revealed to be a special case, arising in regions where gravity is gentle and spacetime nearly flat. Black holes expose the deeper truth that time is a dynamic feature of the universe, responsive to its most powerful forces. As this understanding grows, black holes continue to stand as silent monuments to the flexibility of time. They mark places where the universe reveals its deepest rules, showing that even something as familiar as the passage of seconds is shaped by the vast and subtle architecture of the cosmos. As the story of black holes and time draws toward a close, what remains is not a single conclusion, but a reframing of how time itself is understood. Black holes do not simply slow clocks or stretch seconds. They reveal that time is not a fixed background against which the universe unfolds, but a dimension shaped by gravity, motion, and structure. In their presence, time becomes something that can differ from place to place, observer to observer, moment to moment. What feels steady and universal in everyday life is, on cosmic scales, remarkably fragile. Near black holes, the shared agreement about past, present, and future begins to dissolve. Two observers can witness the same event and disagree profoundly about its timing, its duration, or even whether it has fully occurred. This is not a failure of measurement, but a reflection of how deeply time is woven into spacetime itself. Black holes show that time is local. It belongs to paths through the universe, rather than to the universe as a whole. Each world line carries its own rhythm, shaped by gravity and velocity. Near massive objects, those rhythms diverge dramatically. Far from them, they settle back into something that feels smooth and predictable. The familiar flow of time experienced on Earth is not the rule, but a gentle exception. In confronting these ideas, physics reaches the edge of what can currently be described. Inside black holes, time may lose its conventional meaning entirely. At singularities, known equations fail, and the future of time itself becomes uncertain. Whether time ends, transforms, or continues in some hidden form remains unanswered. What is clear is that black holes expose these questions with unmatched clarity. They also serve as bridges between theories. General relativity describes how time bends under gravity. Quantum mechanics governs the smallest scales of change. Black holes sit at their intersection, forcing both frameworks to confront one another. Any future understanding of time must pass through this terrain, shaped by what black holes reveal and by what they still conceal. In the wider universe, black holes quietly influence the timing of cosmic events. They shape the evolution of galaxies, regulate cycles of growth and decay, and persist across eras when most structures fade. In doing so, they become markers of deep time, stretching moments across spans that dwarf human history. Seen this way, black holes are not merely destructive objects. They are teachers. They show that time is flexible, contextual, and inseparable from the geometry of the universe. They remind us that the present is not the same everywhere, that the future does not arrive uniformly, and that the passage of seconds depends on where and how they are measured. By studying black holes, physics uncovers a deeper truth about reality. Time is not something the universe moves through. It is something the universe creates, shapes, and transforms. Near black holes, that process is laid bare. Seconds slow, histories diverge, and the familiar order of moments gives way to something far more subtle. In the quiet depths of space, black holes continue their work without spectacle, bending space-time and reshaping time itself. They stand as enduring reminders that even the most familiar aspects of existence are governed by profound and sometimes surprising laws. And in understanding how black holes affect time, we come a little closer to understanding how the universe measures its own unfolding.